Okay, so how's everyone doing today? Everyone had a good weekend? How was the video? Any issues or any comments to make it better? Okay. It looked dark on my TV for some reason, but it's one of those things where I'm doing it on an iPad, so the screen is so bright, so it feels like, so I need to see if there's a way to optimize that a little bit. So,
Do you need to turn on a spreadsheet on Blackboard or something?
so the hybrid topics, just to kind of, it's not technically graded homework. I'm grading it via the class participation part, which is about 5% of your grade. So the point to doing it is to learn, right? Learn by doing. I think of all the forms of learning, whether it's reading, writing it down, listening to it, the one that people learn by far the most from is actually doing it. So those activities, the more you do, or the more that you have time to do, I think the better you will be for it. You'll get to learn the details. This is true with just about any job too. You know, as soon as you might have like a certain competence with the skill, like you might go work as a programmer for somebody, and you know how to program, right? Because you've been in college for a while. But then what ends up happening is that you'll find it's a learning curve, right? You're getting to know their systems, and you're not very good at it at first. So even though you may have a lot of head knowledge, there's a lot to just like the practical, like when things don't work. So like a lot of what you learn in physics class is accurate, right? That's how things work for the most part. But then as soon as you do anything in real life, you're like, wait a minute, my equation looks the same as the math book or my physics book, but it doesn't act the same way, you know? So we're actually going to find that out. Oh, I guess I have graphics for us. Let's erase this real quick. Okay. So I did want to talk real quick about the pitch, which is due next week. And to be truthful, I can't remember if I just had the AI class do their project pitches a week early, or if I'm having you guys do yours a week late. I'm thinking of having you guys do it a week late. So that was an oversight on my part. I didn't feel right after it had dismissed and we were talking about on Thursday to be like, let's upset the weekend and make you guys do something unexpected. So I decided it would be better just to delay a week, because it's the pitch is important, but that's obviously not the meat and potatoes of your work. So we can move it a little bit ahead. It would have been easier just to say, oh yeah, we're doing it on Thursday. Yeah, but Thursday we're not even here. So okay, so I did want to talk a little bit about the pitch. So what I think what I'd like you guys to do is we have a small enough class. I think we could talk about the ideas in the Slack channel, and you know, we can get some feedback on what you want to work on, and you know, what are some components to making a good project. From the AI class, we're kind of going through the you're always, nothing's ever smooth, so you're always going, it's like, oh, I didn't explain this well, or I didn't explain that well. So we want to prepare for the pitch. So I think in hindsight, a PDF is the best way to go, because all I'm doing is converting the PDF, and then so we'll do a single PDF slide, 16 by 9, and make sure we have a project title. So that's part one, is project title, a short description of what you want to do. So that way we don't have like a whole session full of simulations and animations pitch, you know, and we see that variation, 8 different fonts but we don't know what you're going to work on. So let's go ahead and so we want to come up with a nice title, and it could be. And this is why we want to talk about it now, because sometimes I always feel like the research project it's in peril almost as soon as you start the class, because you haven't learned the rest of the class. And a lot of times you're in a class because you don't know what the class is about or what's involved, and because you're always starting at the more fundamental concepts at the beginning of class, you don't even know if you're going to have enough time to learn the really fun stuff at the end of the class, you know. So like anybody who wanted to work on rigid body dynamics, I'm sure is like, oh, they're teaching at the end, so I have to learn it myself, you know, if that's the case. And fluids are kind of in the middle, so you have a halfway chance, but then there's like all the basic physics stuff at the beginning, so that seems like pretty easy. We'll all do particles. Maybe I should study this as a professor, just kind of like, do people pick the topics mostly taught at the beginning, the middle, or the end of the class? That would be kind of funny to see if it was almost, you know, and then there's always that metaphor about, you know, babies walking before they run, but actually it's babies run before they walk. That's kind of funny. So maybe we should just start with the advanced stuff, and then it'll sink in. Hopefully it'll sink in towards the end. Always downsides to everything. All right. So in the Hybrid Topics video, we were going over what a simulation loop is. And I wanted to introduce the idea of state vectors earlier on than what the book talks about them, just because it's a really convenient way of thinking about a whole bunch of objects in the scene. And then we started looking at integration, and we used basic Euler integration. However, what was the one problem with Euler integration? One glaring flaw.
It doesn't produce the correct answer.
Not initially, right? I mean, but is it how far off is it though? I mean, it's pretty close.
I don't know. Wasn't one of them really 10% inaccurate? I mean, like, I don't know if 10% is close to you.
Well, it gets better as you decrease the time step. It's not continuous. This is true. However, does it need to be continuous? Now, here's the example I would give for does it need to be continuous? It depends. It depends, because we have an easy way of checking the answer, right? So we start off with, so just to get into the Newtonian physics, we have force equals ma, and we want to find out, well, what's the velocity, right? So just ignoring that force and mass are proportional to each other and all that. Just ignoring, we know that acceleration is, you know, some form of, you know, meters per second squared. So if we want to find out how fast we're going to go, right, velocity is meters per second, you just plug it into the equation. So v equals, you just integrate acceleration with respect to time. And a lot of times you might have a certain time step. So maybe we're going from t0 to t1. We have some, we want to find out how is our velocity changing over time. So if we integrate this, just generally we'll find out that we get, well, that's a simple integration. It's just a times t, and then you just go from your t0 to t1. So a lot of times, if you're doing it an indefinite integral, though, you can just say, we're starting off with some initial velocity. We don't know exactly what it is. So we might say that we have v naught plus at. Okay. So now we know no matter what the acceleration is doing, or if it's constant, then we can calculate the velocity. And then you do the same thing for if we want to find a position, right? So we just throw all of that. So whatever our velocity is plus our a times t. And then same thing here, we'll find out that our x equals some initial x value plus the current, whatever the velocity is, times time plus 1/2 at squared. So So with respect to the Euler one, right, we can at least check. We have the convenience of being able to say, well, I know that I'm modeling my velocity in little time steps, kind of like you're doing a Riemann sum or something like that. And Euler is kind of the same idea. You're just kind of adding up all the areas of all the little rectangles under the curve. And so we can at least check our answer. But in many cases, there is no like handy formula. In fact, I feel like this is about as far as it goes with a lot of the physics that we want to do. This is the most checking we can do because everything else is a function of time. And for a lot of stuff, even acceleration might even be a function of time. Because nothing is ever, like if you're going to jump, right? I might be standing still and then I jump, but I guarantee the acceleration wasn't like suddenly, 5 meters per second squared or whatever it might have been. It went from 0 to 5, but over the period of time, as I'm using my muscles, first it's going down. So I have a little bit faster than gravity. So I'm accelerating faster than gravity is going down. And then I'm going up. And I'm going up enough so that the acceleration is actually more than gravity because I have to leave the Earth in order to do that. So even this one can get a little squirrely depending on what you're trying to do. I was watching a video on YouTube. A game developer conference will repost videos from presentations that they've had, and one was about jumping, the physics of jumping. I thought, oh, that's exciting, because if you do game dev or something, and you're like, I want to recreate, you look at like different variations of Super Mario Brothers, and Super Mario 1 does not feel the same as Super Mario 3, and I think maybe Super Mario World feels really good. It's closer to 3 than it is to 1, but they all have like a different feel. And then if you're like Princess Peach, Super Mario 2, then you're floating on there for a little bit. And so they have, different physics models. But the idea was our tendency sometimes as programmers is let's just put it out there and then just tweak parameters until it feels right. And so the premise of this video was like, okay, well, how about we just put the math down first and then see if we can't calculate what all those constants ought to be, right? So if you have platforms at a certain height and you want the jump to feel like a fast jump or a slow jump, how should you set gravity? How should you set velocity so that it feels the way you want it to? So I thought that was interesting. Okay, so let's take a look at the simulation loop. I just kind of roughly copied one of the versions inside the book. Okay. How many ways do you think there are to do a simulation loop?
That's the ways to do a loop.
Okay. How might you do? What are some ways that you think you might do a simulation loop, or what are some factors involved in picking the way that it's done?
Well, this one wants a constant time step. It looks like it's taking the time delta and then looping.
Right. So H represents the value of the time step.
Yeah.
Okay. Anybody else?
If you want to get really fancy, you could have it increase the time step if you have more objects on screen or something.
Okay. So maybe you're trying to meet a certain performance objective, and if you have 1,000 objects on the screen, you might need to adjust the time step than if you had 100. So in other words, you can adjust the precision. All right. What else?
But you have to have a time step. Right? You can't do anything without a time step.
You need one, yes. Well, unless you do this, you don't need a time step at all. You just say, from the beginning, this is where we're supposed to be.
I mean, you could do the crazy thing, assume the time step constant, and then when it's not, that'll feel very crazy.
That is one choice. So use a constant time step. So we talked about a variable time step, we talked about a fixed time step. You can tie the time step to FPS. That's one of the, I mean, if your game is reliable, right? If your game is going to maintain that kind of frame, it's not a half bad idea to be honest with you, right? It's simpler. It is simpler, right? Sometimes simpler is better than complicated.
If you have a target console rather than very PC hardware.
Sure. So maybe you have some ways that you can do that. I mean, when you can predict what something's going to be, that can make it easier to plan for. So, but sometimes simpler is better than nothing, because what if somebody said, in order for you to do graphics, you have to learn how to do path tracing first, like making the really high realistic images first, before you can even do graphics. How many people would be doing graphics nowadays? Not very many. I think that when you set the barrier too high, you don't jump in there and start working on it. It doesn't have to be perfect at the beginning, but the simpler you can make it, right? Like if I was teaching my son how to do some basic physics, I probably, I'll be honest, I'm not going to nest a simulation like this. If I'm teaching him, I just, we'll just say this much time has passed, and if it runs slow, then it runs slow. If it runs fast, then it runs fast. And using the FPS is at least a way of controlling how fast it goes. In fact, you do have to use your frames per second in this kind of configuration, because especially if you only have a single core processor, right? Which a lot of games are written that way, where you just have everything done in the main thread. Which, if you add threading, that complicates it even more, because now you got to synchronize memory buffers and where are objects, and now I got to lock a mutex before I'm updating all the object positions, and then unlock it, and then it becomes really complicated. Okay, so in this particular case, we might say, well, how much time has elapsed since the last frame? Because sometimes if you're running too many objects, it just drives your frame rate low. And so what you could do, though, if you find that it's way easier, because you're trying to avoid, I accidentally drew a bad frame and it took 1 second, and then everything starts jumping around like crazy, jumping through walls, the whole 9 yards. And so maybe the way to do it is just say, well, our maximum time step is, say, 1 millisecond. And every time we come to our simulation step, then we'll iterate 1 millisecond at a time. That way we can get the results we're looking for. However, if you do it 1 millisecond at a time, that means you're doing 1,000 physics updates per second. And then and we were talking about precision issues. Sometimes maybe it's nice to have a small time step, but then on the other hand, there are some alternative ways of doing it that you don't get the same problems. So what was the one method we were talking about that seemed to kind of eliminate the error? Yep, averaging the previous and the post velocity, and that seemed to work. That works because the acceleration is constant in that particular case. But as with anything, what's a good approach? You have a problem. What's a good approach to start out with? Starts with an M. It's an M word. What's that? That's very close. It's very close. You have a problem. What's the first thing you should do?
I think it's a displacement style problem. Take the or something.
That's getting in a closer direction. We measure. We measure. How big of a problem is this? Right? A lot of times, since we like to fix problems that really don't mean anything. Right? So, measure. Find out how much of a problem there is. Maybe there's, it's like when you're evaluating program performance. Now, you could take it from the approach, I'm going to optimize as I code. So, but the problem is that what if your optimization is not doing it, has no effect because some other aspect of the code is taking so much longer, it's almost like you're getting something for free. You know, this happens a lot when you have when you're doing your graphic shaders, and you have the CPU stuff that causes slowdown. So you might, maybe the problem is you can't transfer enough information from the CPU to the GPU, and in which case you're CPU bound. It doesn't matter how fast your GPU is; it can never get enough data to get it to its maximum performance. The second thing it might be is it might be vertex shader bound. So you're spending so much time doing stuff with geometry, like animation or something, that the fragment shader can't be busy, can't draw enough pixels. In which case, that could be a blessing in disguise, because you're like, well, I've always wanted to do some kind of physically based shading, and it turns out we have all this extra time to do physically based shading because the vertex shader is so busy doing animation. And so sometimes what people like to describe that as getting something for free, right? Because if you, it'd be like if you were in high school and you got dropped off at the mall, and not that this mall in particular is anything to talk about, but you know, if you only had like, if you know, if you knew she was going to go shopping at the grocery store and it was going to take her 10 minutes, well then it's going to be a short mall trip. But if it was going to take her 2 hours, like, I got 2 hours to kill all by myself, you know, or with friends or whatever. So the case is, it's like getting all that extra time for free when normally you would just been like, well, no, you're not going at all. We got to go to the store, only be in and out. and then that's how it is. So same idea here. As far as a simulation loop, circumstances will dictate how much time you have allotted to doing physics. Some of it is determined by how much physics processing you have versus how much graphics processing you have. It could be that your physics calculations are so intensive that your graphics, you know, you have to pare it down way, you know, just to even have something worth showing, right? If you can only simulate 100 objects, then you can kind of scratch off, I want to show 10,000 objects. You know, on the other hand, if your physics calculations are fast, and then and you can simulate 1,000,000 objects, but then your graphics card can only draw 10,000, you're like, well, I've always wanted a perfect excuse to get a new graphics card. So you just go and buy yourself a new graphics card, and you're like, yes. It's always fun to get excuses like that. So this is one of, I think, a really effective way of helping control the accuracy of a physics simulation. Now, I think it matters more, or it really plays an impact with collision detection, because if your time steps are arbitrary long or short, then this one helps make sure that you don't actually miss collisions that could have been missed otherwise. So if the time step's too big, then it could be that an object jumps through another object, and there's no way to really detect that very easily unless you specifically test for that. Whereas if you slowly time step a collision, you'll know that you'll never miss it because an object can never move fast enough to move through something else. So there are some aspects that if you control a simulation loop, you can kind of control another dependent variable. But if you have control over that dependent variable, like objects going through other objects, then that can help simplify it, right? So, because now you don't have to write a general purpose collision routine that measures, like, as an object's going through time, is it going to miss another object? And they kind of cross paths with each other, and they never even get a chance to collide. Okay, so state vectors. So we talked about this being an efficient way of storing many objects. What are your thoughts on state vectors?
Storing data about an object. As long as we aren't in a situation where we need to do something exceedingly clever because we have way too much stuff, sure. Why not?
Are there any benefits to using a data structure like this? Benefits or negatives? Go positives and negatives.
Depending on storage, you might be running into a lot of cache hits and misses, which is not going to be fun for simulation. Depending on whether your CPU better, GPU better, blah blah blah, etc. But whatever method you store it in, you're going to want to try and have a in compressed, not compressed, but a contiguous of the memory, so the cache is trying to grab chunks
Right.
of it all at once.
Yeah, so cache actually was one of the things I was thinking about. One issue that you get with object-oriented programming sometimes is when you encapsulate too much, you have a bunch of objects everywhere in memory, and then you're just iterating through each object, and then you cause all these cache hits. And then you turn your billion operation per second processor into a million operation per second processor, which is like operating a computer from the 70s and 80s. So cache hits are one of those things. That can be a positive, right? Because state vector can be very tightly coupled, and you can just stick it in an array and then just go through it. But what are maybe some what issues can you maybe negative downsides?
What's the alternative?
Alternative is put the state in the objects that they belong in.
Okay.
That could be one, right? So you think about a modern video game, each character might have like its own state vector built in, but then it's kind of, if you have lots of objects and you've fragmented memory a little bit. Two, you might have different data structures representing different kinds of state vectors. In other words, you might have one that just has the position and velocity and the acceleration, but that it doesn't have any rotational velocity and acceleration. And then you might have some that are got different physical properties. Like sometimes you can't get around it, like a fluid simulation is obviously you can't really use a state vector to represent a fluid simulation. So maybe the type of object you're trying to simulate, you have different kinds. So then now if you're trying to, or like collision detection, right? If you represent a sphere different than you represent a cone or something, then now you're writing, you have to deal with the combinatorial explosion of interactions you could have. Whereas this makes sense if you kind of say that all objects are going to share this kind of general framework, then you can throw everything into a state vector, and then you're only dealing with objects of one type with each other, and it's not like a bunch of different kinds. So, yeah, and then but another downside is the information is far from could be potentially far away from where it's attributes that it needs to be applied to. So you have a bunch of if you're loading up a bunch of characters, right, and those are data structure somewhere in memory, then your state vectors might be somewhere else. But you might have a performance increase by doing it that way. So you could put like pointers and stuff back and forth, but in a way you're optimizing the problem, right? But sometimes there is immediate, it makes sense to do it this way because that cache hits and all that stuff are really big, really important. You'll never get to simulate 1 million objects if it's using the cache poorly. All right? Okay. So, state vectors. Now, the book, when they talk about state vectors, they're kind of going later on, but they add things like for particles. So when we get into particles, this is going to matter more, but we might have all the forces in there, all the velocities. Later on, we might want to add color or other things that we might want to render the object with. Those are other elements of state vectors. So it makes sense for some concepts there. Okay. Another thing is that you could probably efficiently use some kind of acceleration structure. So maybe you use it in, let's imagine you're trying to simulate a galaxy, all right, and you have 1 million particles in there or more. Well, if you do the basic Newtonian, there's that equation that governs what the force is between two objects in space, right? Now, if you suddenly want to accurately simulate a galaxy, you have to technically calculate the interaction, the force of gravity between every single star with every single star. So in real life, that actually happens. But in a computer simulation, now you have to calculate, what, 1,000,000 times 1,000,000, 1,000,000,000,000 things? You'll never be able to see that in real time. It's just not realistic because you have an n squared. It's an n squared algorithm to do that. So sometimes what you do is you'll just say, well, let's put everything in a bunch of voxel grids, and we'll simulate each block separately, and then we'll calculate the relationship between the blocks and each other. And so that's a concept of using state vectors in a way where you can kind of group them up. That way you can accelerate some bigger structure by creating an approximate object of what's going on. So to illustrate that idea, right, let's say 4 here, we'll just make it on. Okay. So instead of trying to simulate every single interaction, maybe what you do is you divide it up. And I'm just kind of arbitrarily drawing boxes. But now what you can do is you can say, all of these stars, let's calculate what the interaction of this group, this group, this group, this group, and this group is on this whole group total. And then we can just say, well, every star is affected by each one of these boxes. And then we drastically reduced complexity. All right. Now you'll never get down to n, but maybe you can get down to n log n or something. So now instead of it taking a trillion times amount of, a trillion operations, it takes a billion operations. So now you're working in a realistic space of where we're doing, our processors are running at a billion gigahertz, or running at a billion cycles per second. Now you're actually in the realms of, we can actually simulate this in real time. You can apply it to a GPU, and now you have like that order of magnitude increase. So now you can actually maybe watch it in real time, which I think is cool. Because the other option is, well, just you have to cut down. Instead of 1,000,000 stars, you have to do 1,000 stars. And then you can do n squared and get 1,000,000, which is then something you can work with. And then the other thing too is if you have 1,000,000 stars, I guarantee your cache is not going to work with 1,000,000 stars. You're going to have terrible cache hits unless it's like really organized in a certain way. The cache hits are going to be a big element of slowdown. Okay, so state vectors are an efficient way of storing many objects. Now, we kind of talked about the integration issue and about using the average, and we were talking about Newtonian physics. But what I wanted to do was work with the example program that we had, and let's see if we can extend that and add maybe some more interesting, maybe we could add wind and air resistance to it. Because I think that's kind of an interesting concept. We like to we don't just want to have like a simple object falling and bouncing. So maybe we could have wind be a factor and also have air resistance, and then I think we'll have that'll be enough to cover for today. But part of adding these kinds of things is you'll notice over here. So let's we have that wind is some function of this variable, or the force of wind is some variable d, some constant d times the velocity of the wind. Okay, so same thing with air resistance. It's normally some variable that is, and that's inaccurate, but it's normally some function of velocity. The force is some function of velocity. In other words, if I'm going at 10, and what's going to happen if this variable is very low, like close to 0? What's going to happen?
The air resistance is close to 0.
Yeah, if this variable d, let's think about what happens with this variable d. So we have the velocity of the object, and we have this variable d. That's what's going to happen. It's kind of like drag, but that's kind of like the idea there. Now this is a very simplified model of drag or resistance, but what's going to happen if we set this variable down to a low number, close to 0? Very little. So I have very little effect. Okay, and then if it's close to 1,
Cancel out.
it's going to come to a grinding halt. So I was actually reading there because one thing that I found is that sometimes you get used to putting arbitrary numbers into a simulation so that it feels right. But then what ends up happening is you're like, wait a minute. What is a realistic number? Like I was playing around with index of refraction for rendering, and I was, you're trying to get certain effects, and so you're like playing with the index of refraction, and you're like, well, let's set it to 5 or 10. Which, if you're just doing a plain graphics thing, because you're trying to maybe do Fresnel reflection or something, you're trying to calculate how much light should be reflected, and you're just arbitrarily applying numbers in there, like it's some artistic control. How much refraction do I have, or how much reflection do I have due to the Fresnel effect? Like you're trying to simulate water, right? And you're like, okay, let's throw a number of 10 in there, a number of 5 in there. But then, so I'm going and I'm like, okay, well, wait. Before I do this, what are realistic numbers like? Because part of the motivation for doing this is I was trying to simulate the reflection of like metal. Okay, so and really to kind of get reflection numbers that are kind of closer to metal, you really would have to throw some really high reflection, really high index of refraction in order to kind of get that function to work. Okay. But then I was going back because I knew the diamond was like 2.42, and that really is kind of getting to the upper limit of a dielectric is a diamond that's got a really high Fresnel index of refraction. So then I was like, that's kind of got me interested in index of refraction, and I realized that what I'm doing is I'm trying to use a dielectric equation when there's a separate equation, and so it wasn't realistic to just throw in a high number for Fresnel, or not for Fresnel, but for the index of refraction in order to approximate the Fresnel effect. I had to use a completely different approach. Okay, so part of that has to do with the model was wrong. Okay, so a lot of times what you have to do at the beginning of a problem is you have to determine whether the model is correct or not. Okay, and then when the model is correct, then you can look at the values for different parameters and you can pick appropriate values for those. And then what you can do is judge the performance of your simulation based on its response to plugging in realistic values. And if you plug in realistic values and your simulation is accurate, then you should see a realistic result happen. Okay? So for example, I was looking at
Did it work for you?
the
Change the model.
I did, and I found out like the index, the refraction. There's a different version of Snell's law for metals, and there's a different function for Fresnel reflectance. So it's a lot more complicated. And there's like a really long version, and then there's like a shorter approximate version. And I was like going through textbooks, and I'm like ordering book after book. I'm trying to find out why isn't this just written down. So I actually did some. I was able to basically work my way all the way back to using Schlick's approximation, but the key is you have to calculate the initial Fresnel and the F naught accurately, because if you don't do that accurately, then the whole bet's off. In fact, I don't mind taking a tangent here. This can be fun. Let me see.
Simulated rays.
It is physical light transport. I think I have it easily accessible from here. So the research I was doing here was to accurately simulate Fresnel reflections, but do it in a way that it makes sense for the monitor that you're looking at. Because for a while, you know, your monitor is sRGB, and that's just what it is. But now we have all sorts of different kinds of models. So make it pose. I can make this dull, and when you use the right equations, it looks pretty good. I think it looks pretty good. My big thing is I wanted to make gold, so we get gold, and I wanted to make copper, which copper can be very interesting. Copper is very strange, so I was quite pleased, and I don't know how it looks on the projector. So it's pretty good on the projector. But here's what happens if you don't use if you don't take into account. And actually, what I can show you is I can show you the the full equation. I think this is the full equation. It's a little slower. Let me pose this again. All right, and then that's the Fresnel. That's the approximation. And then this Schlick's approximation. But there was another method, and it was overestimating what the reflectance ought to be. And I was really trying to find out why is that? And part of it has to do with whether or not you're accurately calculating the correct red, green, and blue, and whether or not you're it's not enough. Like, so at first you're like, okay, red, green, and blue. But what wavelengths of red, green, and blue? So then you're like, okay, well, let's just look it up online. And then you're like, okay, well, because I guess you just go to Wikipedia, right? You could just say, let's, or you could just say, right, what are the wavelengths of red, green, and blue? And so you might get some ranges of, say, violet or 450 to 495. In some cases, you'll go and where was the one where you go to like a physics website, and this has a range, but some websites will just say it's this is the value for red and this is the value for green, and so on. But then I decide, well, actually, what's the wavelength of light coming off the monitor? Because that's the one we need to model. We want to make sure we get the accurate one. So it turns out, like, if you change, and let me click on this. If you change this, if these are all in the values, like these are all in the normal ranges, right? But if I do this wrong, that can make copper look like it's red, or you could almost make it look like gold. How did I do it? Yeah. And I was like, well, that's no good. You can really tell, actually, with gold. You can make gold look like copper. And technically, 520 is not far off. I think our eyes are like 550 is, I guess, as you get closer. This green really makes a big difference. And this is a big factor in when you're doing simulation, because let's turn the green down. So copper, So even though we were in the ranges of blue, green, and red, I didn't like go outside the range there. It's not like I'm making it up. But if I went outside the range, then, well, the monitor is displaying red as a certain wavelength, green as a certain wavelength. So if I'm not matching the wavelengths for the monitor, then this can cause an issue. And I'll give you an example here. So let's turn that off. So let's say we're doing this accurately. But instead of sRGB, we use Adobe. And so if you've ever taken pictures of it within the Adobe profile, it has more green in there. Theoretically, it's actually a different wavelength for green. So if you're not careful with how you approach the color space, then all of a sudden now your gold looks like copper on a different monitor. So the idea here is that if you have this on and you're using an Adobe calibrated monitor or using an Adobe color spec, then it should look the right colors. And then you have the new DCI, this Digital Cinema Initiative, P3. So, and even they have slightly different, like one's for theaters and one's for like home. And they're pretty close, and they're also pretty close to sRGB, but they're a little bit different because the white space is a little bit different. And then they're also got more color saturation too. So technically, the greens, reds, and blues theoretically could be more intense. So sometimes you have to just be careful how you model it. I was talking in my last class too that sometimes in graphics you think of color as red, green, and blue, but that's not right. That's not always the case because the visible spectrum, you know, red, orange, yellow, green, blue, indigo, violet, and RGB, right? Violet is violet. It's not red. And so if you have your object and you say, my object is red, but the way that your eyes process color, you know, when violet hits your light, well, the science says that your eyes respond to red, green, and blue. Like that's where it's most sensitive. So you can actually kind of figure out where the eye is most sensitive. And so, because it used to be like, if you look at art, that the primary colors, and really if you mix primary colors, you get any color you want. But it used to be red, yellow, and blue were primary colors. So if you're a painter, you might be familiar with red, yellow, and blue, and then that's how you mix colors, okay? But when they were doing the, the science earlier on in the 1900s, they're figuring out that actually you're really sensitive to the rods, the cones, and all that are sensitive to certain types of light. So what ends up happening is that we use RGB for computer monitors because our eyes respond very well to that. However, if you use red, green, blue, and you're trying to, let's just say you have an object that's a red object, which means that it absorbs all the other frequencies of light, right? And it reflects red. Well, if you shine violet light on this red object in real life, what should happen? What's that?
You should get red light out.
No.
I mean, is it composite light or is it just violet?
No, just violet light.
Oh, okay.
In real life,
Oh.
you shouldn't see anything. It should be dark. But what color is violet in red, green, and blue? You can go with like hot magenta if you want. It's red and blue. So what ends up happening is if you shine a violet light on an object in graphics and you're using red, green, and blue, well then the red will reflect. But that's not physically accurate. So you always have to be careful with the model that you pick to make sure that it's appropriate. Okay? Now when we're talking like Newtonian physics, this is actually pretty straightforward. It's not like there's too much craziness going on, right? It's pretty straightforward. Okay, so this is an example of this is my like personal example. It kind of represents a journey of a few years of investigating the Fresnel reflections. Fresnel reflection, and kind of going, okay, this doesn't work. Just setting the Fresnel, just setting certain things to be arbitrary values, that doesn't work. So this is things you can learn by experience. Because I tell you what, as a programmer, especially if you like doing games and stuff, it's so easy just to just throw this number in. If it feels good, we'll go with it. You know, who cares what that number is? as long as it works. And I guarantee you, in real life, you will always see this like pragmatic approach to things. Like, well, if it works, we're just going to go with it. And sometimes you don't have time to make it better. You just go with it, even if you don't understand why it works or why it doesn't work. So anyways, I go back to say that when you have a problem, the first thing you should do is measure. First of all, find out where the problem is. What is the root cause of the problem? And then go about and try to fix those causes, right? That's how you solve a problem. You got to fix the cause of the problem. You can't just put a Band-Aid over the problem. Okay. Oh, and I even have graphs on here. So we can actually see what happens if you. So let me turn that back to sRGB. So here is the red, green, and blue response to the reflection. Okay, so that's gold, but if I pick like silver, you'll see that first of all, silver has a little bit of a yellow reflection because you got a dip in the blue. But then if you pick something like titanium, that's different. Although it's a lot closer. Zinc, a lot closer. Okay. What about aluminum? That's almost straight. So these are what we call like white metal. Okay, but if you're experienced looking at metal, you'll look at silver, and a lot of people say silver will tarnish over time and it'll yellow, right? And that's because of this effect. Actually, what I found is that the color of metal it's almost entirely determined by its index of refraction, which is really cool. You don't have to guess what color metal ought to be. It is what it is because of the way that how it reflects light. And so here's a case. So here's what I'm doing here. The black line represents the index of refraction. So we know the index of refraction is going to be smaller, right? We're not expecting unrealistic numbers. But then what you have is a complex. It's a complex index of refraction. You have an imaginary number associated with it, and that we call kappa or K. And this is what causes the each metal. You can record the spectrum, and so this represents red, green, and blue. So this is the electromagnetic spectrum. So you can see the response over time. So if we were to switch to gold, you'll see that the index of refraction changes significantly as you get towards red, and it goes up. The complex goes up. So what ends up happening is you have high reflectance of red and low reflectance of blue and green. And if you look at the difference between gold and copper, you'll notice that it just kind of shifts a little bit, which is why copper looks like copper. Okay, this is where the monitor values of red, green, and blue. So if I switch to Adobe, you'll see the green shifts over to the side, and that's why you have to use a different value to approximate it. Okay, so going back here, so yeah, so this was fun. Actually, this is a good example of a research project, right? Where we're really trying to focus on finding why things are a certain way. And this is a paper that actually got published last year in the Czech Republic. So I thought that was cool, that I was able to kind of determine what factors makes Fresnel, so the display is a factor. So if you don't accurately do Fresnel, then the display will change your results in an inappropriate way. But then I also am able to show, like if I do Schlick's approximation and the actual Fresnel, you'll see that the differences, there is some difference using the approximation, but there's different like if I use different approximations, then it's not as big. But if you just use Schlick's approximation by itself, you do get errors technically. But visually, you can't tell the difference because of the way that the light is. It's not linear. It's a logarithmic response. Okay. That's the tangent. Okay, my personal experience with just starting out with picking our arbitrary values and not fully understanding what's going on, partially because it's limited understanding. It was because of ignorance. I didn't really know any better until I kept, trying and trying and trying and trying and trying to find out why isn't this producing, an accurate result. And now I feel like I really understand Fresnel reflection. That's bonus points there. I really feel like I understand that. Okay. So we're going to try and add air resistance and wind. Okay, but we're talking about these values for D, and that's when I got sidetracked. Okay. But what I thought was interesting was the book was talking about accurate values. Okay, so who's ever seen The Absent-Minded Professor? Flubber. Flubber. There's a new one, and then there's the old one. I like the old one. It's the better one. The one with Frank McMurray. There was the Flubber. Yeah, Robin Williams. That was. Is this the floating car? Well, he had a floating car, but maybe it was called Flubber. Did he?
No, the Flubber.
Oh, that's what it is. It's been a while since I've seen the movie. Good movie though. Okay. Anyways, getting sidetracked here. Repeatedly sidetracked. Okay. So here it was. All right. So one of the things that we're talking about now. Who remembers friction from physics? Everybody. Okay. So I didn't put the friction equation here yet. I'll add that in the slides so you guys can refer to that later. But did anybody remember the variable? Mu. How am I remember mu? Maybe it's because I took physics twice, and so it just burned in my mind. I took it in high school, AP Physics, and I took it again in college. And I got more out of the high school class for some reason than I did probably because I was in high school every day. Monday through Friday we had an hour, and so I felt like I really learned physics in that class. There's mu. That's the Coulomb law or friction model. So it's mu times F. You have different directions for friction and forces and stuff. Okay, so this book, and so what I'm basically teaching you is we're using like an approximation. We're just saying what should the we're going proportional to the velocity, right? So if we say a value of 1, then we're saying the velocity doesn't change at all, right? And if we start decreasing that, then we can go all the way down to 0, in which case the friction causes it to come to a grinding halt, right? Because it's like whatever velocity you're going, you're not going that anymore. Okay, so accurate values. Okay, so if you're using the Coulomb friction model, then if you're using like Teflon over Teflon, then your mu values are like less than 0.05. So very, very small. So friction is just like how much loss do you have. This is why we don't use the Coulomb friction model right now, because it's more of a measure of if you use like 0.05, that means it's very little change. But we're trying to get it in terms of like, well, what is it in respect to the current velocity? Okay, then you have wood on wood, and that will be a mu anywhere between 0.25 and 0.5. And then steel on steel, you might have a mu value between 0.5 and 0.8. And I guess I didn't know this, but if you combine certain kinds of metals, like silver on silver, you could actually have mu values greater than 1. I thought, oh, that's interesting. It's strange. I see everybody's like, that's interesting. That's kind of weird. Like I'm gonna have to Google that later, you know. So Okay, so we're going to use what's called like a coefficient of friction, and we're just basically saying what's the fraction of tangential speed loss. So how much difference do we have? Now, what that means is that the tangential direction, what do we mean by tangential direction? I think it's the horizontal, because friction is horizontal, right? We're moving a box across a carpet, right? So it's the normal sticks up, tangential is kind of along the surface. Okay. So what we're doing is like if we take a look at, because part of this has to do with elasticity, like what's the bounce of an object. So if you have an object, like if I drop a basketball on the floor, and what's the restitution force? Like, it doesn't just change. In some way the momentum transfers to the earth, and then it goes back up into the ball, and then it gives the ball that vertical velocity. Okay, and so if it's an inelastic collision, that's like billiard balls, right? You hit a billiard ball into another one, that ball stops and the other one goes. Okay, and the friction might have a little bit of component in there, but essentially that's an inelastic collision where all the momentum is transferred. But when you're talking about like the earth so big compared to a basketball, then a lot of that energy just goes straight back into the basketball. Okay, so if you were to drop a ball, okay, so we were talking about friction, and now we're talking about elasticity. Realistic values might be, well, first of all, you wouldn't want negative values. That would be kind of strange. And if you have values above 1, that's also not realistic, because then this is, if you remember, we were talking about BRDFs in the graphics class, where we basically said, if your reflection is less than 0, that's like saying you're sucking energy out of the whole system, right? You can't just subtract energy if you want. You can't destroy it. And then if it's greater than 1, then we're saying it's not conserving energy. In other words, you can't add more energy out than you get in. So we always want the C value for elasticity to be between 0 and 1, because you can't remove any more than you have, and you can't add any more than you have. So, so values for that, if you were hitting a baseball on a wood surface, then your restitution value is going to be about a little over 0.5. And then if you're dropping a tennis ball, that's going to be anywhere from 0.73 to 0.76. And then if you drop a basketball, it's actually required to have a restitution of between 0.82 and 0.88. So basketball is supposed to bounce by a certain amount. I guess it's like football gate, the football is supposed to be filled. It's kind of silly to me, but it's these people take these things seriously. People have gone to court over this. They take their air pressure seriously, and that's actually part of the FIBA Central Board. I guess it's a basketball association. Okay, so realistic values. So the idea here is that if we want to add this to our simulation, we would like to be able to plug in realistic values and expect to see something similar. So if you're writing a baseball game and you're simulating a batter hitting a baseball, then in your physics, then you probably want to stick 0.5 in there and then see that might give you a clue in, well, how fast is the player even swinging the bat? Well, if you know that you have to use a force of 0.5, and then you can kind of backwards figure out, well, my velocities for my bat should be about this, right? Because you know that, is it 400 feet, or what's the distance from home plate? What's that?
There isn't a standard.
I know there is no stand. Well, there kind of is, right? But it depends on the wall height. Your ability to hit a home run depends on how high the wall. That's why, like, the Green Monster is famous because it's so high. It's hard to get a ball over that side. But then you go. But then, depending on how much money you have to build a stadium, you know, it might be a fence, you know. So your high school typically doesn't get a lot of money to build the Green Giant, you know, or I mean yeah. So anyways, so this is a good way, you know, so you want to plug in realistic values to see if you're getting realistic results out. All right. Okay. So we talked about the coefficient of restitution, and then we were talking about friction. And I think that the way, so if you're using the Coulomb friction model, then you use that mu value as a function of your velocity. Okie doke. Because I do want to, so just to, I mean, the hybrid topic for this week is collision. So next week, we're going to talk a little bit more about how do you incorporate friction as a component. But for right now, let's add wind. Okay, let's add wind and air resistance. And if we have time, then maybe we could add like the object kind of falling from the sky into water. And we know that the resistance would change for that. And in a way that works the same way like with the atmosphere, right? You're going to have a different air resistance close to Earth than you will up high, and you know, but of course, so there's lots of factors there. Okay, so let's see here. I did it again. I'll close that. And let's close all that. And let's start up our light server. Okay, so we had the popping blocks example. So what I'm going to do here, we want to kind of spend some time, right, looking at how do you actually do this stuff. So I'm going to copy example 3. Now it's all example 5. And I need to adjust we'll call it windy blocks. Let's go and update our description. We don't need to do anything to the shader, so that's kind of nice. Just can stay in here. So let's go ahead and move. Let's just make this full screen. Okay, so one thing that we haven't done is we haven't done any kind of acceleration. Like we didn't calculate the average acceleration, which I think we would want to do. So let's see what accumulate does. It doesn't return anything. So maybe we could say let v0 equals, or v before equals our state vector, and we need to clone that. Okay, and then this represents the after. So let's let v equal, add it to before, and then scale by 0.5, so let's take the average. Something doesn't seem right. Is that guessing right? Something doesn't seem right. We'll go for it. We'll go with it anyways. And then we'll use our doesn't appear like we broke anything. Okay. Sometimes it's nice. It's completely makes no sense at all, but sometimes it is nice to actually like use variables that say what you're trying to do. Okay, so over here we can I have this comment here, but we can see that we're trying to the average of after and before. I'm going to try this out. I'm pretty sure that, yeah, that's fine. Okay. Okay, but what we need to do is update the forces. Okay, so we know that acceleration equals F over m. Okay, and here's our drag variable. Remember I had added the drag variable to this, but we didn't have any kind of like, there was no rhyme or reason behind it. And we could say wind equals, we're just going to use random numbers here. Okay. We'll just go with 1. Okay, so the equation for doing wind was, well, we basically have d times, or d over m times v, right? Because force of, say, air equals d times v, and the force of wind equals some other value of whatever the wind velocity is. So we actually need to add, I guess that makes sense. The drags could be the same. Okay. So let wind equals let's give it a direction. Let's just call it -1. The wind is coming from the east. Okay. So then if we want to calculate the actual acceleration, right, we're going to have F equals whatever the force is due to gravity plus whatever force is due to air plus whatever force is due to wind. So that's our, if you recall doing state diagrams or these force diagrams in physics, you basically just plot the object and you say, well, this force is coming down. So essentially what we're doing is we're just going to assume that the air resistance has to do with the fact that it's falling through the air. So it's down. So there's our center of mass. And we know that we have force due to gravity. Okay, and we also know we have some force due to wind. And then we also have some force due to air, which is well, if we just think of it simply, we just think of the wind as a crosswind, moving, because we're in 2 dimensions. So the wind is just moving in. Although these are 3-dimensional vectors.
So okay. So I was
Right.
thinking about the air resistance here. So we're only worried about the air resistance as it falls.
As it falls.
Control.
Well,
Because the upward velocity is just right.
Sure. And this is incorporating the air resistance because we're going to use the same value d,
Sure.
just going to do this way. Okay. I guess technically that would be pointing the other way because our wind is coming. Something like that. Anyway, so we know air resistance going up because it's resisting gravity and it's some function of velocity. So it would be, if we're not moving anywhere, there's no air resistance. Wind resistance, oh, that has to do with the actual velocity of the wind, right? Okay. In fact, we'll call this v underscore wind so we don't confuse ourselves. Okay. So we're gonna go ahead and add. We're gonna solve this equation. So we're gonna get g because we know that gravity is m times g, and we're gonna subtract d over m because we gotta divide by mass. And technically, because the air and the wind is the same, we have wind minus v. So the reason why we use minus v is because the air resistance is in what direction? It's the opposite direction. So if we're falling, it's going up, even though our velocity is going this way. So air is whatever direction we're going, it's going the other direction. So this is why we do minus v. Okay, so with that in mind, we can go ahead and calculate. We can say that let A equals we've got negative 9.8 and subtract drag over mass, which we haven't said how much mass our objects have, or have we? I think it's part of the state vector.
Yeah.
We could actually change that now that it's going to make a difference. So that should be the state vector m, and then we multiply that by v wind minus whatever our current velocity is. Oh, and we can't just do minus here. We have to do dot sub. Yes. Well, we could actually say SV dot A equals that. Just replace it. Well, let's see if it crashed. I feel like it feels different. They should be. That's the only thing it's not doing. Unless we're not looking. Oh, we're still looking at example 3. That's cool.
Yeah. I don't know
Oh.
what kind of different we're looking for.
Okay. It's because so we copy and paste the example 5, but technically on the bottom we need to. Okay. Something's not working. That's what that means. So now we debug. Now we debug and see what the console says. Unable to set property of inner HTML. Because we're looking for element description, which is not there. Okay, so what we need to do is go back to this one. Let's just copy. There we go. It's possible that it blew away. So here's what we're going to do. We're going to say that if x is less than, say, -2, then sv dot x equals positive 2. Else, if sv dot x is greater than 2, sv dot x equals -2. This is so. Where are they? Invalid tag name. What's up? Ah, that's fine. Well, one way we could do this is we could just go right here, and we could take a look at our objects. So object 1 is not a number. Good to know. Okay, so we need to figure out why it's not a number. It probably has to do with let's step through this. So wind, that's correct. Okay. Our state vector, let's make sure our velocity is not okay, let's, can I edit that? Zero, 0, 0. Okay. Let's see what happened to our A value. Nope. One of these messed it up. It's the fun stuff of debugging why the stuff's doing this. Okay. So let's put 0, 0, 0. And let's go to the next. So make, pretty straightforward. Sub, let's get some more screen space here. Oh, how did V end up being? Oh, that'll work. Yeah, that's not going to work. Okay. Sometimes you just get used to having operators. There.
So it seems like it keeps speeding up. The wind continues to speed up until they're just automatically at 2, right? So
Right.
Go back to going at 2 and never go.
Okay. Well, that was cool, though. I mean, at least we have an interesting result there. Okay, so now we just go back and we check our math. Okay. So sometimes, in this case, you just gotta like let just make up names as we go. So we have G minus, well, I don't think that's causing the issue. Oh, it's because we set drag equals to 1. Okay, so let's set drag to like some small number. See what happens. Well, that does affect how they can't fly high, they can't fly low. Okay, let's go halfway and see what happens. This is baseball bat, remember? It's kind of fun seeing it take off. Such a spectacular way. I'm curious about this. I'm curious about the velocity. Like, if relative velocity versus the wind. Unless we just have well, they're using like 12.5. I mean, that makes sense. Should just be able to say that the wind is moving. I guess if it's moving 1 meter per second, does that seem like a high? Over here they use an example of negative 12.5.
It seems like for the increasing acceleration, which makes me think that it's updating SVA instead of resetting it every time.
Well, we should be resetting every time.
Right, that's what I'm saying.
Yeah.
Might, yeah, but it's not resetting.
The only thing I can think of is that our velocity here. Is this supposed to be, yeah, gravity plus d over m times wind minus our current velocity? Unless I need to be doing this. Maybe this is what the problem is. Oh, I think that it is. Where's the... Let's make sure we have the parentheses right. Okay. We should be adding gravity, not subtracting gravity. Now it's... Okay.
Yeah.
That looks good. Just in time for us to quit. Okay, cool. So now we have windy blocks. They're just kind of bouncing around like tumbleweeds. That's cool. Okay, so now we have like gotten the physics thing to be a little bit more interesting. Okay, cool. All right, so the hybrid topic for Thursday, we're going to start covering collisions, so we can kind of make these maybe bouncing balls that have some kind of elasticity to them. And so those are kind of accurately, so they're not bouncing around like popcorn. Right now we're just setting a random velocity going back up as soon as they go below the ground plane. And then it might also be interesting to have like water, and then them having bouncing in the water and out and so on, and kind of get a little bit more complex, like simulate like a really simple fluid. So we've maybe changed the drag based on whether or not they're in or out of that pool. So, okay, sounds good. Yeah, let's go ahead on Slack. Let's go ahead and start talking about our projects, and that way we'll be all ready for next Tuesday. And we can also talk about the schedule for presentations. Okay, so I'm going to go ahead and stop the stream.